In this lecture, I will introduce you to a class of optimization problems known as linear programming problems. Let me begin by giving you a few historical facts about the subject of linear programming. The term linear programming dates from now 1947 may not be the exact date, but anyway it was around that time from 1947. George B. Danzig, while working for US Air Force, formulated the program planning procedures used in the US Air Force as a problem of optimizing a linear objective function subject to a finite system of linear equations and inequalities in a finite number of variables. He also found an iterative procedure for solving this problem, which he called the simplex algorithm. This was not the first time that concept of linear programming was used. In 1939, Kantorovich, a Russian mathematician, formulated production problems of optimal planning as a linear programming problem and proposed effective methods for their solution. In fact, there is an interesting story that Danzig went to Kantorovich and very proudly tried to show that he had come up with this simplex algorithm and he had formulated this problem as a linear programming problem. Kantorovich opened his drawer and took out his own formulation of this production problems, production planning problem as a linear programming problem, and he showed his own algorithm for solving it. Independently in the US in 1941, a prototype of a linear programming problem was proposed. So, last 70 years have seen tremendous theoretical and computational developments in linear programming. We hope to give you a glimpse of this wonderful theory, its applications and developments that have taken place since its inception. Just on if I go back to the first slide, I would say that the date was 1944 or 45 when Danzig actually proposed the linear programming problem and method of solving it. These class of problems follow axioms of linearity, which I will try to introduce you, and they have been very successful in formulating and solving a large class and variety of problems through these linear models. So, I will take up an example to demonstrate to you how these axioms of linearity work, and this problem is known as the blending problem. It was initially introduced by Professor K.G. Murthy. He formulated the problem. The situation is that there is a gasoline company, or maybe we can say a petrol and diesel making company, which has 3 raw fuels. It wants to blend into making 3 it gets a raw material and it wants to blend it into 3 fuels of different octane ratings. The fuel that we use for different vehicles have a octane rating, and we try to determine the price and the market value through these octane ratings. So, now I would like to show you by introducing the problem, the data that we will use to formulate this problem as a linear programming problem. Let us say that the number of barrels, we will say that our decision variable, which I will define as Xij, is the number of barrels of raw gasoline I used for making fuel type J. So, Xij, Ij are the 2 suffixes. So, the first suffix relates to the raw gasoline that is used, and then J is the suffix used for the fuel type J, which is used for making the final product that goes to the market, right. And then Yi will be the barrels of raw gasoline I sold as it is in the market. That means the company has some raw materials, raw gasoline, it wants to blend it into different fuel types, then whatever is left over, that is also sold back, because some people can use, some chemical companies or some people can use this raw gasoline also. Okay. So, I will first show you the data to so, now here if you look at this table, so raw gas type we show under 1, 2, 3, then they have different octane ratings. So, like for example, raw gas of type 1 has octane rating of 86, and the number of barrels available per day is 5050, and the price per barrel is rupees 60. Then raw gas of type 2 has an octane rating of 91, and the number of barrels available is 7100 and cost is rupees 70. So, similarly for the raw gas of type 3, then the fuel blend, that means when we blend these 3 types and then come up with the 3 different kinds of fuels. So, the first fuel, for example, has a minimum octane rating of 95, and this will be, the selling price will be 300 rupees per barrel, and the demand for this fuel is at most 10,000 barrels. So, we have to put stress on the word at most. That means you cannot sell more than 10,000 barrels in the market. So, the company has to keep this in mind, that you cannot, you should not be manufacturing more than 10,000 barrels per day. Then for fuel type 2, the minimum octane rating required is 90. That means it can be more than 90, okay, and the selling price will be rupees 200, obviously, because the higher the octane rating, the higher the selling price, and for this the demand can be anything, any amount can be sold. For the fuel type 3, the octane rating, the minimum octane rating is 85, and the selling price will be rupees 140 per barrel, and at least 15,000 barrels are required. So, the demand is at least 15,000, but it can be more. So, let us try to formulate this problem, and let us see look at the constraints. For example, when we blend the 3 raw gasolines, so my variables are, see, if I for making the first type of fuel, I will use all the 3 raw gasolines, and so my variables are X11. X11 says that is the first type of raw gas I am using for making the first fuel. Then X21 also says that it is the second raw gas that I am using for making the first fuel. So, for making my first fuel type of gas, I will be using the variables X11, X21, X31. So, therefore, then I am saying that the rating for this blend would be 86 X11 plus 91 X21 and 99 X31 divided by the total number of barrels. So, that will give me the octane rating for per barrel, and this should be greater than or equal to 95. We have to again see this thing, because when we specified the octane ratings, we said the minimum octane rating is 95, it can be more than 95. Therefore, the constraint would be greater than or equal to 95, right. And then when you rearrange the variables and bring them all to the right hand side, the final constraint is minus 9 X11 minus 4 X21 plus 4 X31 greater than or equal to 0. So, this is your first constraint, which specifies that the fuel blend of type 1 must have minimum octane rating of 95. Similarly, if you see that the other 2 constraints, which for the other 2 fuels, the octane rating, so the other 2 constraints is the same way we can derive, and we get the other 2 constraints. So, these 3 constraints now say that whatever blend I make has to satisfy these octane ratings. Then we also had constraints on the amount of barrels which are available. So, the supply constraints, so here for example, X11 and X12 and X13 tell you the number of barrels that I used for the first raw gasoline to make up my to make up all the 3 blends. So, the total consumption of first raw gasoline, you can say, is X11 plus X21 plus X13, and Y1 is the leftover. So, the total thing should not be more than 5050. Whatever we have available, I can only use up that many barrels. Similarly, for the other 2 types of raw gasolines, whatever barrels I have available, I can use them up, and so that gives me the supply constraints. Now comes the demand constraints. So, the total amount that the total number of barrels that I manufacture for the first type of fuel add up to X11 plus X21 plus X31, and this should not exceed 10,000. So, that tells us that the demand for first fuel type cannot exceed should not exceed 10,000. So, therefore, we cannot manufacture more than 10,000. Similarly, for the second demand, for the second fuel, since no amount is specified, that means the demand can be anything. So, we will simply say that X12 plus X22 plus X32 should be just non-negative, because whatever amount we manufacture, that can be sold, right. And now this comes the third constraint, which says that the fuel of type 3, there must be at least 15,000 barrels that should be manufactured. So therefore, x13 plus x23 plus x33 should be greater than or equal to 15,000. So through this example, I want to show you that how various situations can be easily modeled through this linear optimization model, as we call them. Any optimization problems where we can apply. And so now, okay, before I say anything more, I would like to come and now let me just spend a little bit of time on the how we formulate the objective function. So the objective function, remember, x11 and x21 and x31 are the number of barrels which were manufactured for the first fuel for the first type. So I'll re-say it, and x11 plus x21 plus x31 total is the number of barrels that I manufacture for type 1. So and the selling price is 300 rupees. So therefore, I am saying that my cost function, which I would like to maximize, that is the company would like to maximize the profit that it earns. So then the selling price, it for the type 1 fuel, it earns 300 into the number of barrels that is manufactured for fuel type 1. Then similarly 200 times the number of barrels for fuel type 2, and 140 times the number of barrels for fuel type 3. Then remember, for raw gasoline, which is more than 91 octane, the selling price for that is 135, and since the cost for the raw gasoline of type 1 was 70 rupees, so the total earning from selling Y1 barrels of raw gasoline of type 1 is 135 minus 70. Similarly, I have the terms containing Y2 and Y3, and then finally the total, for example, raw gasoline of type 1, this should be 60. You can make the correction here, but anyway, by mistake this is typed as 50, so it should be 60 times x11 plus x12 plus x13. Total number of barrels that I used for manufacturing, that I used from the first raw gasoline, is x11 plus x12 plus x13. So similarly, minus 70 times. So the cost of the barrels that I use up, I subtract that, and the first portion, the first few terms give you the profit or the earnings from selling the fuels that the company manufactured, and the last three terms give you the cost price or the money that you spent in buying the raw gasoline. So the difference gives you the final earnings of the company. So this is your objective function. This we would define as a linear optimization model, or a broad term is linear programming problem. Now here, if you look at this, the axioms that we have used, the first one is proportionality. 300 rupees is the price for 1 barrel for selling the type fuel 1, but when I manufacture x11 plus x21 plus x31 number of barrels for fuel type 1, I multiplied by 300. That means no concessions for large scale buying. It happens that when you go for a large scale buying, then you expect, and the trader also gives you concessional rates. But here we are assuming proportionality. That means whatever the cost for 1 unit, no matter how many units you sell, you earn the same income. So it is 300 times. So this is what is known as proportionality. So wherever we find a situation where you can sort of approximate it by proportionality, we would say that we can formulate this problem as a linear programming problem. And the other one is additivity. The axiom that I am using here is, when we blend different raw gasolines, it is possible that some chemical reaction may take place, and so the volume may go down. That means it is possible, but here we are assuming that no additivity is valid, in the sense that if I use 10 barrels of one type and 20 barrels of the second kind and maybe 15 barrels of the other, then the total number of barrels that I finally blend is just adding up all these numbers. So no loss, no chemical reaction is taking place, and no loss is taking place. So additivity is assumed to be valid here, and that's why I could formulate the constraints and the objective function using this axiom. Then the third one is continuity of variables. Now here, of course, in this particular example, my variables xij give you the number of barrels of type I used for making type J fuel. In linear programming, again, we assume continuity of variables. That means xij could be any fraction. So here also I can say that it can be half a barrel or 2/3 of a barrel. So Xij can be a fraction. So these are the three basic axioms of linearity, which are proportionality, additivity, and continuity. And these allow us to write down the formulate the problem as a linear programming problems. And as I will want to repeat it again, that in most of the situations it has been demonstrated very successfully that these linear models are very helpful in solving everyday life problems and maybe many more complex problems also. Okay. So therefore, if you use the matrix notation, I can formulate a linear programming problem as I can write minimize, short for minimization we write min, or your objective function can be a maximization problem. So this would be equal to C transpose X. So here, for example, this is the short form for I am writing Cj Xj summation, j varying from 1 to n. So I am assuming that I have n variables, n decision variables. C's are my cost coefficients. They could be profit coefficients or cost coefficients, depending on whether I am minimizing an objective function or maximizing it. So this will be my objective function, and subject to, in a concise form, I can write the constraints as Ax less or greater this equal to b, right? And then here you see I should have mentioned this also in the beginning when I introduced the decision variables Xij, that either we will use a particular raw gasoline for a particular blend or I don't. So therefore, it's very natural that my variables will be Xj greater than or equal to 0 for all j. So here I have used only one index, but it can be two indices for a variable also, as we saw in the earlier example. Just to simplify the presentation, I am saying that a linear programming problem can be formulated as z equal to C transpose X subject to Ax less than greater than equal to b, which is my right hand side numbers, and then my variables are non-negative. Now in fact, one can write a more general form here. I can write a more general form, and as we saw in this problem, in the blending problem, I can write it as, and let me just stick to minimization, because you see that you can always make it a maximization problem by multiplying all the cost coefficients by minus sign. So this is minimize, this is C transpose X subject to j varying from 1 to n, which is less than or equal to bi, I belonging to I1. This is my index set. So my some constraints may be less kind than the other set of constraints 1 to n were greater than or equal to kind. And finally, I also had some constraints which were my supply constraints, which were equality kind. So j varying from 1 to n is equal to bi, I belonging to I3. And here then my total, the index set, so that means I, which is the addition of all the index set, is I3, and the cardinality of I, that means the number of total number of this thing, can be m. This is common notation, and everywhere we just say that the number of constraints is m, the number of variables is n. Okay. So this will be my general statement of a linear programming problems, and I will now show you how to, maybe we can give it some more this thing I want to talk about. Let me now introduce the concept of slack and surplus variables. Okay. The names are quite suggestive. Let me explain. If you have a constraint of the kind Aij Xj, j varying from 1 to n, less than or equal to bi, right? Just as suppose we had a demand, there was a demand constraint, and it said that the number of barrels produced for fuel type 1 should not exceed 10,000. So let's say this is my demand constraint for the fuel type 1. Then here I will introduce a variable excess I, which is equal to Bi minus summation Aij xj, j varying from 1 to n. So, this is the difference between the right hand side number and the left hand side expression. So, this tells you that when I actually come up with my schedule of how many barrels to use in what fuel blend, and so what is my final production of each fuel type, then it is possible that I may have manufactured more than 10,000 barrels for the fuel type 1, and so excess I measures the difference between I should say it the other way, that the left hand side tells you the number of barrels that you have manufactured for fuel type 1, and it should not exceed 10,000. So, the difference excess I gives you the difference between the 10,000 barrels that is required for fuel type 1 and the actual number of barrels that you produce for fuel type 1. So, this difference is the slack in your first kind of demand. And so, and of course, this will be non-negative, because you are not going to produce, if you want the constraint to be satisfied, it is not going to exceed 10,000, which is, and therefore, so we will say that excess I is non-negative. So, this is the slack in your in the constraint, in the less than or equal to kind. So, the name is quite suggestive. Now, let me handle the constraint of the type greater than kind. So, this will be Aij xj, j varying from 1 to n, which is greater than or equal to Bi. Now, in our fuel type 3, it said that the number of barrels produced should be at least 15,000. That means the demand can be more than the supply for those fuel type 3 can be more than 15,000, but it should not be less than 15,000. So, here if you talk of the surplus variable, excess I, I will write it as equal to the left hand side expression, that means the total number of barrels that you actually produce and the least requirement, the minimum requirement. So, this will tell me the surplus variable excess I in this case measures the number of barrels that you have produced over the minimum demand. Right, and this also we require to be non-negative, so that the constraint will also be satisfied. Right. So, now you see that if I bring this to this side, then this can be written as summation Aij xj, j varying from 1 to n minus excess I is equal to Bi. So, by forcing, if I ensure that my excess I also maintains a non-negative sign, then you see that the original constraint sigma Aij xj varying greater than or equal to Bi will be satisfied. That means, if I have a set of variables xj's, j varying from 1 to n, and a corresponding surplus variable excess I, which satisfy this constraint, then you see that variables 1 to n, x1, x2, xn will satisfy the original constraint. So, I ensure that by keeping the sign of the slack or the surplus variables non-negative, my original constraints will continue to be satisfied. So, this is the idea. And of course, here what we are saying is that there is no penalty attached to either not making, see, in the first case the demand was 10,000 barrels at most. So, if we produce less than that, there is no penalty, and in the third case, in the third fuel, the demand is 15,000 barrels at least. So, we produce more than that, and whatever we produce, we are able to sell it. So, then there is no penalty attached to how many by producing excessive barrels of the fuel type 3. So, therefore, we say that the prices, so then we say that the cost coefficient of surplus and is 0, is equal to 0. So, therefore, we started out with the general form, and I am able to reduce it to, so now the after adding surplus and slack variables, all the constraints reduced to equality form, and so my linear programming problem would be minimize z equal to C transpose x subject to Ax equal to b, x greater than or equal to 0. Now, here the variables include slack and surplus variables also, right, and so this is known as the standard form. Standard form of linear programming problem, of a linear program. For short, I will sometimes be using the abbreviated form LPP to denote linear programming problems, right. So, this is known as the standard form, and now you see that the way I constructed the way I converted the equality constraints to inequality constraints to equality constraints, you saw that, and by putting the cost coefficients of these surplus and slack variables as 0, there is 1:1 correspondence. So, what I want to essentially point out is that the original problem, which I stated as a general form or whatever it is of a linear programming problem, had less than, greater than in constraints. In the standard form, all are equality constraints, and you see that there is 1:1 correspondence between the feasible solutions of the two systems. So, let me give you a definition of a feasible solution for the linear programming problem that we have defined. So, we say that if for a linear programming problem in its general form or in its standard form, a set of values x equal to x1, x2 up to xn for the decision variables is said to be a feasible solution if all the xi's are non-negative and they satisfy all the remaining constraints, the linear inequalities, equalities, whatever the constraints are, also satisfy them as well. So, all the constraints are satisfied and the values are the non-negative, then we say that it is a feasible solution. Earlier I had stated the general form of a linear programming problem. So, the standard form I can write out in detail. The standard form will be minimize z equal to Cj xj summation j varying from 1 to n, then summation aij xj j varying from 1 to n is equal to bi I belonging to I1. I have been able to add slack variables here and convert it to equality system. Then the second set of constraints also reduced to equality system. This will be j from 1 to n is equal to bi I belonging to I2. These were already equality form. I belonging to I3, and I require all variables to be non-negative, j varying from 1 to n. So, this is my standard form, and what I want to say is that there is 1:1 correspondence between the feasible solutions to this system and feasible solutions to the original system. If I have a feasible solution for the original system, then I can get a feasible solution for this system by substituting the values of the original variables in this constraints, in the equality constraints, and the differences will give me the slack and surplus variables. If I have a feasible solution for the equality system, that is the standard form in equality constraints, then by dropping the slack and surplus variables, the remaining variables will be the original variables, and that they will constitute a feasible solution for the original system. So, there is 1:1 correspondence, and since the objective function cost coefficients for slack and surplus variables are zeros, the two objective function values are the same. That means for a feasible solution for the original problem, I have a corresponding feasible solution for the new system with equality constraints, and the two objective function values are the same. So this is now I am introducing concept of equivalence. That is, we have a concept of two problems being equivalent if there is 1:1 correspondence between the feasible solutions, and for optimal solution of one problem I can derive an optimal solution for the other. This is a very useful concept, and you can see that why it is needed right now. I can, as we have seen, that it is always or you may have already experienced that handling linear constraints is definitely easier than handling inequality constraints. So by reducing to an equivalent system, by reducing my original linear programming problem to a system in which all the constraints are equality form, it will be easier for me to get a solution procedure for the system with all equality constraints. So the advantage is there, and as we go on in this course, we will see that this concept of equivalence is used very often, and of course the objective functions for the two problems in this case are the same, but sometimes it is possible that when you have two equivalent systems or two equivalent problems, you can the relationship between the two objective functions may not be so direct. You may have to derive optimal solution for one from the other, but since there is 1:1 correspondence between the feasible solutions, this is not difficult. We can do it all the time, right? So therefore, by adding slack and surplus variables, we have reduced the system of constraints to equality constraints, and we will now try to obtain a solution procedure for the standard form of a linear programming problem. So in matrix notation, I will again now write the standard form of an LPP. So let me say that standard form of an LPP will be minimize Z equal to C transpose X subject to AX equal to B, X greater than or equal to 0, where C transpose, when I say, so originally C is n by 1 vector, the decision variable vector X is also n by 1, right, and your A, the cost coefficient matrix, is m by n, and the right hand side vector, and B is m by 1. That means the total number of constraints is m, the number of decision variables is n, and we can also again revisit the fuel blending problem and say that in that case, of course, it was my maximization problem. So the coefficients of C were your total earnings from selling the manufactured fuel, and then A, the matrix A, is also known as the technology matrix, because depending on the technology that you have, you generate or you obtain, by blending different gasolines, you obtain fuel of a particular blend, of a particular octane rating. So the coefficients in A are they indicate the technology that is being used in your manufacturing process, or even in many different situations you can use them in some other ways. And B, of course, is your right hand side constants, which are, in our case, they represented the number of barrels that were available, the supply amounts. Then some of the components of B also represented your demand, maximum, minimum, whatever it was. So therefore, in a nutshell, the linear programming problem requires you to specify the cost coefficients. There is a given technology through which whatever you manufacturing process you are using, you say that you put in some raw materials and you come out with a final product. And of course, the B can be, and one can, there is no end to the number of situations one can describe where these axioms of linearity can be considered to be valid. You see, one cannot say that very exactly these axioms of linearity would be valid for the situation, but if we find that the error that one encounters is negligible, then and the benefits, that means you may not get a very exact schedule of, for example, in this case how many barrels of each fuel kind to produce, but one gets a fair enough idea, as to how much of this much and how much of that, and one can work around this. So it can be treated as a sort of a guiding tool, whatever the outcome that you get from, suppose if we manage to solve this problem, this fuel blending problem, so it will tell the manufacturer, the decision variables will tell you how much of each barrel of each type of gasoline, raw gasoline, to use to manufacture the final product, and then the manufacturer can of course maybe not use the numbers exactly, because the axioms of linearity that we are assuming may not be exactly valid for the system. So that goes on, but as I said that over the last 50 years these linear optimization models have been very successful, and it has helped people to get reasonably good answers. Okay. So now let me start reviewing a few things before, and of course I will try to discuss a lot of pathological cases that can occur, but first let me review a few situations. So if my problem, as I again have to I will write it here again, which is minimize z equal to C transpose x subject to Ax equal to b, x greater than or equal to 0. So if you simply look at, see, I will now require, so in another way of stating this problem is that you have a number of combinations, that means your variables 1 to n, the variables x1 to xn, these are your decision variables. The constraints are Ax equal to b. So you need to find out the values of these x1 to xn which satisfy these constraints, and the non-negative values only, because Ax equal to b, the system of equations, has large number of solutions, and in fact later on we will also actually count the number of solutions that are possible. So this may have Ax equal to b has a large number of solutions, but all solutions may not have all the components non-negative. So I need, out of the feasible solutions Ax equal to b, I need those which have all components non-negative. That means the components can be either positive or negative or 0, cannot be negative. So the number becomes smaller, and then what I am asked to do is to, out of all these solutions which satisfy these two sets of constraints, I have to select the one which gives me the minimum value here. So this becomes my optimization problem, because it's possible that for the manufacturer of the gasoline there may be many different combinations in which the manufacturer can blend the 3 raw gasolines available to him to manufacture the 3 types of fuels. So these constraints and the demand and the supply constraints are all satisfied, but out of all these possible combinations there will be maybe 1 or 2 which gives you the best cost, best profit. So as I am saying that here I am referring to the problem here as minimization problem, but if I multiply this by minus sign, it becomes a maximization problem. So in general we just like to state the problem as a minimization problem, but there is no loss of generality here. It can be a maximization problem which can be stated also as a minimization problem. So the idea here is that out of all the feasible solutions we want to find one that minimizes or maximizes my objective function. Somebody may say that what a big deal is it? You have a finite number, for example. Okay, if we now try to recall, let me just talk to you as in your school level you have looked at, you know, the rule for finding out, for example, if you want to find a solution to Ax equal to b. Okay, before we talk of finding a solution, let me first say that what is the condition under which. So I need to in order to be able to say that this system itself has a feasible solution, before we want to say that we want to find out the best solution out of all possible solutions here, first I have to know that whether this system itself has a feasible solution or not. And so we need the concept of rank. So rank of a matrix A, there are many ways of defining the rank. This you can say is the, whatever maybe, if you have the definition that you may have learnt is the size of the largest size submatrix whose determinant is non-zero. Maybe this is not very clear. So determinant, NANT, largest size submatrix whose determinant is non-zero. This can also be defined as maximum number of linearly independent rows or columns. So if some of you are familiar with the concept of linear independence, then you know that the maximum number of rows or maximum number of columns which are linearly independent in the matrix A, that also constitutes the rank of the matrix. And of course the two definitions are equivalent. I am using the word equivalent here again. So you can say that the corresponding submatrix with the larger, so if this is the maximum number whatever it is, then you can find a corresponding subdeterminant of that size whose submatrix of A of that size whose determinant is non-zero. Okay. So once, if you know that the rank A is whatever it is here, and we also know that this has to be less than or equal to M, because if it's a maximum number of linearly independent rows or columns or the largest size submatrix, then this cannot, here I am assuming, see again this I should have pointed out earlier, and that is that your M is always considered to be less than N. That means we say that the systems we handle here under linear optimization models are underdetermined systems. That is, the number of constraints is always less than or equal to the number of variables. Because if you have large number of constraints, then it is possible that you have restricted the system so much that you are not able to find a feasible solution. So by practical experience, and also it has been noticed that in practical situations we are trying to formulate optimization problem, the number of constraints always is less than or equal to the number of variables, and so underdetermined system. So here if I say that the rank is less than or equal to M, I am assuming that M is less than or equal to N, right? Okay. So then this gives you the rank, and we say that the system AX equal to B has a solution if rank A is rank A comma B. That means if I consider, and this is called as the augmented matrix. So here I have added extra column. That means this new matrix is my, so that means your A comma B is M by N plus 1 matrix. So this is the augmented matrix. So we say that the if the two ranks are equal, then the system will always have a solution, and vice versa. And which again, if you want to, if I can use the language of linear independence, all it says is that if rank A is rank A comma B, then B, that means, can be written as a linear combination of the columns of A. And this is what we are saying. We are saying that if this system has a solution, then you are able to write B as a combination, because you are able to write, if I break up my matrix A into columns, and this is A1 x1 plus A2 x2. So A1, A2, An are the columns, right, n columns. So then this xn is equal to B. So when I say that this system has a solution, that means I can find x1, x2, xn such that this linear combination of the columns of A is equal to B. And so obviously, since I am saying that the rank of a matrix is equal to the maximum number of linearly independent columns, therefore, B cannot be independent of the columns of A, because if the system has a solution, then B should be expressible as a combination of the columns of A. But in this case, we are wanting more. So therefore, this is the condition. So when you formulate a problem as a linear programming problem, if you are looking for, if you want the system, if it's a feasible formulation, then this should happen, that rank A is equal to rank A comma B, right? And then we want something more. What are we saying? We are wanting a solution for which x is also non-negative. That means we are not simply saying that B should be expressible as a linear combination of the columns of A. We want that B should be a non-negative linear combination. That means the scalars x1, x2, xn that I use for writing B as a combination of the columns A1, A2, An, these should also be non-negative. That will constitute a feasible solution for my linear programming problem. Okay. So this is what we are looking for, and as I said that here the task that lies ahead of us, that means we have to design an algorithm to locate feasible solutions to the system Ax equal to B, which have all components non-negative, and then we have to find the best solution out of all these. And this is what we will go, and therefore you see that here it is so convenient to have equality constraints, because I have a nice characterization of feasibility here. Of course, feasibility for Ax equal to B, then I have to modify that characterization, or maybe design the algorithm in such a way that I only locate the feasible solutions for which x is non-negative. That means all the components are non-negative. So this is the task that lies ahead of us, and towards we will let me state the problem again. Minimize z equal to C transpose x subject to Ax equal to B and x non-negative. Okay. So here, in case the problem does not have a feasible solution, the algorithm will detect that and tell me that the problem is infeasible, and therefore there is no question of looking for the best, because I stop there once I know that the problem is infeasible. If the problem is feasible, then of course the attempt would be to locate the one which gives me the best value in terms of either a max or a min. I will conclude this lecture by just recalling all that we have discussed today. Essentially, I tried to introduce the axioms of linearity, and I told you how by using these axioms of linearity we can formulate certain optimization problems as linear programming problems, and then I tried to show you what task algorithm will have to accomplish in order to be able to solve a linear programming problems. I started discussing a little bit of the required mathematics behind it, and in the next lecture I will continue with the formulation of the algorithm and show you the various features of the algorithm which will solve linear programming problems.